Welcome to Calc Chapter 33. Today we're going to be talking about inverse trig, exponential, and logarithmic derivatives, as well as what linearization is and how to use it. Our first big topic of the day is kind of something that we've seen before. We know what an inverse function is. So we can recall that the inverse of f of x is, we write that f to the -1 of x. That's our inverse. And so when we are taking the derivative of inverse functions, we have this special rule that kind of helps us evaluate those derivatives at specific points. So when we have an inverse function, let's say y equals x plus 1. So when I find the inverse, I switch the variables, so I get x equals y plus 1, and then I want to solve for things in terms of y still, so I get y equals x minus 1. So y equals x minus 1 is the inverse of y equals x plus 1. And if I plug in 5 for x, here I get 5 plus 1, y is 6. Here if I plug in, let's say 6 for x, 6 minus 1 is 5, and that gives me my y. So when I take the inverse, I kind of have these two numbers that flip-flop. So f of a, I'm going to rather use this because this is in the definition. F of b, so f of our 6, that's the same as saying the negative inverse of, or the inverse of f of a. So basically, when I take the inverse, my 2 points kind of flip-flop. So I'm still looking at the same point. We can write this f of 5 equals f inverse of 6. So I'm just flip-flopping the points, that's all. So I have this special rule that we can use, and we say that this should all be in parentheses. The derivative of the inverse at a is equal to 1 over the derivative of your regular function at b. So let me repeat that. The derivative of the inverse at any point a is equal to the derivative of your regular function at your point b. So again, in this example that I gave above, our a in this case would be, let's say 5, and our b in this case would be 6. So I would find the derivative of y equals x plus 1. The derivative of that is just 1. So this one's kind of an easier one. And then I would find the derivative of my other one, y equals x minus 1. The derivative of that is also 1. And then I would evaluate that at 6. I would evaluate my other one at 5. So I say 1 equals 1 over 1, and it ends up matching up. So this is our rule just with any given particular inverse function. What we're really going to be focusing on are these trig identities. So there are a few that you have to memorize. You really don't have a choice. And so we got 3 mainly. So tan of negative, the inverse tan of, we just say u because we need to use the chain rule with this. The derivative of that is equal to 1 over 1 plus u squared times du dx. The derivative of the inverse of sine, so arc sine, oh, this should be u, sorry, of u is equal to 1 over the square root of 1 minus u squared times du dx. And then our last one we have to know is secant. And we say this is equal to 1 over the absolute value of u times the square root of u squared minus 1 times du dx. And the important thing to note with sine and secant is that we need the absolute value of u to be, oops, sorry, for secant, let me erase this real quick. Secant, we need the absolute value of u to be greater than 1. Sine, we need the absolute value of u to be less than 1. And that way we don't get into imaginary numbers. So these are the rules for the following inverse functions. We're going to walk through a few examples of these together. So here's our first example, the derivative of the inverse of tan of 5x squared. So I know 1 plus d squared du dx, and so my u is going to be 5x squared. So all I need to do is plug this in. So 1 over 1 plus 5x squared squared times the derivative of this, our du is 10x times 10x. So you can simplify this if you want, but we'll get 10x over 1 plus 25x to the 4th. So this is really all it is. We're just kind of plugging in whatever is inside your tan, that's your u. And so basically just plugging that into our formula. So here's a DIY problem. You can try at home, finding the derivative of the inverse of sine of x squared. So go ahead, look back at that identity, try to see if you can do this by yourself. And so this is what you should have gotten if you tried it by yourself, 2x over the square root of 1 minus x to the 4th. So now we have 2 more derivatives to really go over, and that's a to the x and then log base x. So if we remember correctly, which we should, the derivative of e to the x is just e to the x. And I'm going to write this as times 1 because this goes along with our rule. This actually follows our rule. If we think about ln of e, that's equal to 1. And so the derivative of a to the x, where a is any number, is equal to a to the x times ln of that a. So this is our derivative rule for a to the x. So we can use this with any base a. We can see kind of how it works with e, because ln of e ends up being 1. So that's for our a to the x. The derivative of log is a little bit more complex. So the derivative of log base a, and they write this as u, is equal to 1 over u times ln of a times du dx. So these are 2 of the new ones that we're going to have to be able to use when finding derivatives as well as integrals. So here's an example where we're asked to find the derivative of 2 to the x minus 3x. And so again, we're still just using our basic derivative rules with the adding and subtracting. And so I can take both of these derivatives separately. So the derivative of 2 to the x, as we learned from the last slide, is 2 times ln of 2 minus the derivative of 3x is just 3. And so this is our final derivative. So this one's a little bit of a tricky one. We have to use actually 2 different rules when we're doing this one. So go ahead, see if you can try this DIY. It involves the log as well as the exponential. But yeah, see how far you can get, and I'm going to pause it real quick so that I can write down the solution for you. So like I said, this one was a little tricky, but basically what we have to do is we have to end up using chain rule. And so this is kind of the step-by-step process. If you simplified it, you should have just ended up with cosine x. So take a look through, make sure to note any questions that you have on this one in particular. So the last thing we really have to talk about is linearization. And I struggled with this in high school and college until one of my professors told me that this is basically a Taylor polynomial. So linearization is just an estimate. It's an approximation of f of x. We are just using a first order Taylor polynomial, and this is called just linearization. So this is our formula for linearization. Like I said, it's just a first order Taylor polynomial. So when it asks you for the linearization approximation, this is what it's asking for. So here's an example of a question that they might ask, very similar to the questions that we've been dealing with in class with series. So it asks, find the linearization of f of x equals cosine x at x equals pi over 2 and use it to approximate cosine of 1.75 without a calculator. So basically what we've just been doing with polynomials, we first construct the polynomial and then we can use it to approximate a value that is kind of close to our a value. So first we need to find just our regular, so our f of x equals cosine x. We're just going to go through the same process as we do with our Taylor polynomials. F prime is f sine, or f prime is negative sine. And then f of, we are focused on pi over 2, f of pi over 2, that is equal to 0. And then f prime pi over 2, that's negative sine, and that's equal to -1. And so our linearization formula, we take our f of a, which is 0, plus our f prime of a, which is -1, times x minus pi over 2. So this looks like just negative x plus pi over 2. So when I want to approximate 1.75, I'm just going to plug in 1.75 plus pi over 2. And that's my approximation. So again, this is just basically using our first order Taylor polynomial and to do what we've been doing. It's just a different question. They just asked it in a slightly different way, find the linearization, and that's how we'll see it kind of in the future. So this is it for Calc Chat today. Please make sure to write down any questions that you have. We're going to be just kind of going over these problems in class. There's no ABC problems today. But please make sure to like and subscribe, and thank you for watching.